All right, let's dive right into this, explainer. Welcome. Today we're taking a pretty fascinating journey to explore exactly how humanity learned to observe, measure, and actually move through our world. It's a story that goes from utter, absolute confusion to crystal clarity.
I want you to think about something for just a second. How far is it from Delhi to Lucknow? Or, on a much grander scale, how far away is the actual moon from the Earth? Everything in physics, and honestly, in our everyday lives, connects back to how we observe and measure the space between 2 points. Whether you're just figuring out if you can walk to the market, or if you need to engineer a spacecraft, you're fundamentally asking a question about distance.
So, here's our roadmap for today. We'll start with the story of transport, look at the measurement problem, explore the standard metric solution, and finally, wrap up by understanding types of motion. Let's get into it.
First up, the story of transport, going all the way from walking to literal space travel.
Early on, we didn't have any means of transport. People moved exclusively on foot, literally carrying goods on their backs. Later, we started domesticating and using animals. When it came to water, early boats were just simple logs of wood with a hollowed-out cavity. But over time, humans got smarter. We started putting pieces of wood together to imitate the streamlined shapes of fish. Then came a massive game-changer, the invention of the wheel. Carts pulled by animals dominated for thousands of years, right up until the 19th century gave us the steam engine and railroads. Fast forward to the 20th century and we've got motor cars, supersonic jets, and, crazy enough, spacecraft that can actually drop wheeled rovers right onto the soil of Mars.
All right, moving on to Section 2, the measurement problem, or as I like to call it, the absolute chaos of subjective measuring.
Let me share a quick, kind of funny story from our source text about two students, Paheli and Bujo. So they share a single desk in their classroom, but they are constantly arguing over who is taking up more space. To solve this, they decide to measure the desk using pieces from a traditional game, a gilli and a danda. They find the desk is exactly 2 dandas and 2 gillis long, so they draw a line right in the middle. Perfect, right? Well, a few days later, the line gets wiped out, and Bujo realizes he's lost his old gilli danda set. When he brings a brand new set to measure it again, the desk is suddenly no longer 2 dandas and 2 gillis long because the new pieces are a totally different size. They're left with this tiny fraction of space completely unaccounted for. Chaos ensues.
Now, humanity actually faced this exact same problem, but on a massive global scale. Historically, people just relied on their own bodies to measure things. They used the length of a foot, a pace, a cubit, which is the length from your elbow to your fingertips, or an angle, a single finger, and even a mutthi, or fist. You can imagine the absolute confusion this caused. I mean, if I sell you a yard of cloth measured from my outstretched arm to my chin, and my arms happen to be way shorter than yours, you are going to feel completely cheated.
Which brings us nicely to Section 3, the standard metric solution, finally bringing some much-needed order to the world.
The fix finally arrived back in 1790 when the French created a unit of measurement called the metric system. To get everyone on the same page globally, scientists adopted what we now call the International System of Units, or SI units. We officially replaced those highly variable cubits, feet, and paces with the standard meter, centimeter, millimeter, and kilometer. The tool that brought order to the world is beautifully simple, the standard scale. And the exact breakdowns are super easy to follow. The SI unit of length is the meter. 1 meter is divided into 100 equal centimeters. Each centimeter is then divided into 10 millimeters. And for those really huge distances, like going from Delhi to Lucknow, we use the kilometer, which is exactly 1,000 meters.
But it's absolutely crucial to actually know how to use the scale correctly. Like, what if the end of your geometry scale breaks off, and you can't clearly see the 0 mark? Well, you should never, ever just guess where 0 is. Instead, step 1, just avoid that broken end entirely. Step 2, start at a clear, full mark, like the 1.0 centimeter line. And step 3, if the other end of your object lines up at, say, 14.3 centimeters, you simply subtract your starting point. 14.3 minus 1.0 gives you exactly 13.3 centimeters. It is literally a foolproof way to ensure absolute accuracy.
Now, obviously, rigid, straight scales don't work for everything, right? I mean, try measuring the girth of a large tree or your chest size with a stiff plastic ruler. Yeah, impossible. We have to adapt to curved lines by using flexible measuring tapes, or even just simple pieces of string. You just run the string along the curved path, mark it, and then measure that stretched out string against a standard meter scale. You can even fold the string into halves, quarters, or eighths to get really precise fractional measurements.
Okay, let's head into our final part. Section 4, understanding types of motion and how things actively move around us in that space.
Scientists basically classify all the physical movement around us into three primary categories. There's rectilinear motion, circular motion, and periodic motion. Understanding these three really unlocks how we view everything, from a falling apple to a spinning planet.
First up is rectilinear motion, and it's exactly what it sounds like. It's motion where an object moves strictly along a straight line. Think of a sprinter running down a 100-meter track, vehicles driving down a perfectly straight highway, a stone dropping straight to the ground, or soldiers marching past in a parade. The path is direct, it's forward, and it's completely linear.
Next up, we have circular motion. In this type of motion, an object moves, but its distance from a fixed central point literally never changes. If you tie a stone to a thread and whirl it around your hand, that stone is moving really fast, but it's forever trapped at the exact length of that string from your hand.
And this brings up a really fascinating point. In circular motion, the object as a whole might not actually be traveling across the room. An electric fan stays perfectly still on your ceiling, and a clock stays right there on the wall. But if you mark a point on the blade of that fan or the tip of the minute hand, that specific point is continuously traveling in a circle, maintaining the exact same distance from the center.
Our third major category is periodic motion. Basically, this is motion that repeats itself exactly after a fixed interval of time. It's got a rhythm, a specific cycle, almost like a heartbeat.
You actually see this everywhere in everyday life. A classic pendulum swinging left, right, and back again. A kid soaring back and forth on a playground swing. The needle of a sewing machine furiously pumping up and down while the wheel turns. Even the membrane of a tabla vibrating when it's struck, or the strings of a guitar being plucked. They all repeat their motion over a set, reliable period.
Now here is where the physics gets incredibly fun, because, well, the real world loves to multitask. Objects can actually have combined motion. Take a simple ball rolling across the ground. It is moving forward in a straight line, right, which is rectilinear motion. But to actually do that, the ball itself is constantly spinning around its center, which is rotational motion. It's literally doing both simultaneously.
So we've gone all the way from walking barefoot to landing rovers on Mars, and from measuring with a random elbow to utilizing the flawless standard metric system, which allows us to accurately track objects spinning and swinging through space. As we wrap up this explainer, I really want to leave you with a quick challenge. Look around the room you're in right now. What types of motion and measurements are happening right next to you? Do you see the periodic swing of a clock pendulum? The circular motion of a fan? Maybe the rectilinear path of a bug crawling across the floor? The physics of motion and measurement is constantly unfolding right in front of your eyes. You just have to know how to look at it. Thanks so much for exploring this with me today, and hey, stay curious.